All right, so our main topic for today is the metric system. And so the metric system is actually in the middle of chapter 2 in your textbook. The first part of the chapter gets into scientific notation and numbers and measurements. And we'll actually talk about those things on Friday. The reason I wanted to cover this today is because in your PLTL sessions, either this afternoon or tomorrow afternoon, you're going to see a lot of metric and metric conversion stuff. So I wanted to make sure you had some exposure to it before I just threw you into an activity that was all about that stuff. So as far as measurement goes, in the sciences, we tend to use what's called the SI system. The SI system goes by a number of different names. We probably think of it most commonly as the metric system. And the SI system or the metric system is founded on a few base units. The base units, there are 7 of them in total. For this class, we'll focus primarily on just 4 of them. So the base unit for distance or length is the meter. The base unit for mass is the kilogram. The base unit for time is the second. And the base unit for temperature is Kelvin. And so these are the 4 primary symbols for those base units. Now, like I said, there are other base units that exist, but for the most part, they're not going to be things that we are going to talk about explicitly here. There's really no reason for us to do so. Now, you might be looking at this list and going, well, those are kind of interesting units to choose. Why these particular units? And where is a unit like volume coming? Well, volume is not considered a base unit because we can derive volume from these other units. I think about the volume of a cube. I wanted to take the volume of this Kleenex box. I would take length times width times depth. Those are all 3 measurements of distance. Distance times distance times distance to get volume. Well, that doesn't make it a base unit. That makes it a unit that is made from base units. So we have a different name for those. So that's why some of the units that we're kind of most familiar with aren't here. Now, another interesting kind of characteristic here, the kilogram for the base unit of mass. Why the kilogram instead of the gram? Well, that has a lot to do with some other units that we're going to use eventually. So when you get into force, when you get into energy, the units for those are newtons and joules. And newtons and joules use kilograms as their unit for the mass component of that conversion. Another important note to consider as we are starting to think about units, in the sciences, we often talk about mass. The kilogram is a measure of mass. And by definition, mass is a quantity related to how much matter is in a substance. And from that perspective, the mass of an object does not change from place to place to place. So if I take the mass of an object here on planet Earth and then transport that object to the moon, it's going to have the same mass in both places because it's going to have the same amount of matter in both places. Where it's different is when we start to think about, well, what is the effect of gravity on an object? Well, here on planet Earth, we have a certain gravitational force. The gravitational force has an acceleration of 9.8 meters per second squared. On the moon, there's a slightly different gravitational force. It's lesser. And so while two objects may weigh the same, or excuse me, may have the same amount of matter, may have the same mass, they're going to have different weights. Same object is going to be heavier on planet Earth and lighter on the moon. And so when we take the measurement of mass, we're usually actually measuring weight. Now, so if I go to the lab and I measure out the mass of this marker, unless my balance has been calibrated to remove the force of gravity from the calculation, it's just going to measure the weight of this object. We're going to call it mass. We're going to give it in mass quantities, but it's really weight. So there is a fundamental difference between the two. So if we get on technical terms, weight is all about gravity. The more gravity that is present, the more an object is going to weigh. Mass is independent of gravity. This object is going to weigh the same, have the same mass, regardless of where we weigh. So mass is a consistent value for an object. Weight is not. Weight varies based upon gravity. And one of the reasons we can't fully put that into context is even here on planet Earth, there are slightly different gravitational forces depending upon where you are. So we use the terms interchangeably. Technically, they're not fully interchangeable. As I mentioned before, the reason we have only those 4 base units for consideration is primarily because most other units can be formed out of those 4 units. When we have a unit that is built from base units, we call it a derived unit. So a derived unit is formed from other units. Most common of these is volume. Volume is a measure of space. It's a derived unit. And again, we can go through this because to find volume, we basically take distance and we multiply it by a different dimensions distance. And we multiply that by a different dimensions distance as well. And so if all of those measures of distance are base units, meters times meters times meters, cubic meters would be the official volumetric unit for that particular set of measurements. Now, in talking about derived units, we have to understand that we are not limited just to the base units for making those. So, for example, if I don't want to measure this tissue box in units of meters because it's kind of absurd, this tissue box is nowhere near a meter long, I can measure it in centimeters, I can measure it in millimeters, I can measure it in a number of different ways that make more sense. But I would still be taking distance times distance times distance to get that relationship, to get that volumetric measurement. The only difference would be what is the unit that I am cubing. If I measure everything in centimeters, centimeters times centimeters times centimeters, I would get cubic centimeters. If I measure everything in millimeters, millimeters times millimeters times millimeters, I get cubic millimeters instead. They would all be considered volumetric units. And so anytime that we have that distance unit squared, or excuse me, cubed, anytime we have that cubic distance, we're going to be talking about a volume. And that's not exclusive to just things that are boxy. That gets into other kinds of objects as well. So if I want to look at the volume of a sphere, one-third pi r. I want to look at the volume of a cylinder, trying to measure, one of these guys. Pi r squared for the circle part times h for the length part. That would give me the volume of the cylinder. So all those geometric kinds of formulas that you learned in math for determining the volume of different kinds of objects, they would be useful in this kind of way if I was trying to measure the volume of that object in that way. Now, you'll learn in lab, there are other ways of determining the volume of an object other than just simply measuring its dimensions. That's a different story for another day. The main feature of the metric system, we talked about the units, we talked about the base units, we talked about the derived units. The other key aspect of this are the prefixes. Now, the prefixes allow us to put multipliers on our base unit to talk about how much bigger or smaller our measurement is compared to the base. And so we can start all the way at the top here, the prefix tera, which would have a meaning of trillion. Well, a terameter would be 1 trillion meters. Now, I don't know how to put that into context or how long that is actually, but let's just go from, it's a really stinking long distance. Of these units, now we've seen different versions of these units in different kinds of ways. Tera, giga, mega, these find their way in a couple ways. We talk about computers in terms of capacity, in terms of memory, in terms of hard drive capacity. The words tera and giga show up a lot in those. When we talk about radio frequencies, laser 91.1. What is 91.1? That's a measurement. The measurement of the wavelength that radio signal is broadcast at, 91.1 megahertz. But probably most common for us out of this group is kilo. We have the most context for kilo. Many of you have ever run any kind of a race. You know that the distances for track and field are measured in meters and kilometers, usually. You might have different names for them. 1,600-meter race is sometimes referred to as the mile race. It's not quite actually a mile, it's a little bit longer. We might come up with other names for them. A 5K, a 10K. K there stands for kilometers. So kilo, we have some base of understanding. We know what that is. We've seen measurements of it. The other ones here, like I said, yeah, we know tera, giga, and mega from different kinds of measurements, either broadcast signals, computer capacity, memory, hard drive capacity, those kinds of things. Hecto and Giga, or Hecto and Deca, you see them occasionally, but their uses are not terribly common. And maybe they were a little bit more common once upon a time, but not as much even so now. You know, very few applications. Maybe a hectacre, where we're talking about a 100-acre plot of land, but even that's pretty limited in its application and its use. On this side of the ledger, where we have smaller quantities, these ones can tend to be seen a little bit more. Again, thinking about things in terms of distance, we generally know what a centimeter is. We generally know what a millimeter is. Micro and nano have found their way into kind of just popular discussion. Maybe not in the proper context always, but we know that they mean something small. Pico and femto, we'll see these occasionally when we start talking about things on the atomic scale. Pico and femto become a lot more useful in those kinds of discussions. But for the most part, most of where we live is really in this part of the scale. And so if I look at my overall kind of scheme here for the metric system, there are really only 5 of the prefixes that I really have to have an intimate need-to-know knowledge with. Kilo is 1,000 times the base unit. That means that a kilometer is 1,000 times bigger than a meter. That means a kilogram is 1,000 times bigger than a gram. And I need to know centi, milli, micro, and nano. Those are the ones I need to know the most urgently. And I also need to know that these are fractions. So a centimeter is 0.01, 1/100th of a meter. One way to kind of flip this around is if you want to think about it the opposite direction. Instead of thinking of a centimeter as 1/100th of a meter, you can flip it around and say that there are 100 centimeters in a meter. There are 1,000 millimeters in a meter. There are 1 million micrometers in a meter. There are 1 billion nanometers in a meter. Those are the things that we want to think about. That's what we want to kind of frame ourselves into as we're looking at these different metric prefixes and how to use them. All right, here's a question for us. Let's say that we take a measurement, and the measurement tells us that whatever we are measuring is this many meters, 1.2 times 10 to the negative 10th. Now, I could talk about that in terms of meters, but let's be honest. 1.2 times 10 to the negative 10th, that's a hard number to kind of contextualize. I got to think about, okay, I've got to move that decimal to the left 10 times. So it's 0.00000000012 meters. Okay, I know that's small. I'm having trouble kind of putting my head around, well, how small is that? And so one of the reasons we use scientific notation, and we'll talk about scientific notation on Friday, is to help us with a little bit of that context. The other thing that we can think about, though, is, well, why use meters? If my measurement is that small on the meter scale, Why don't I change it to one of the metric units that isn't that way? And so if I go back to my scale here, I look at nano and I look at pico and I say, okay, 10 to the negative 10. Where is that? Left between these two, which one should I use? Should I rethink that measurement in nanometers? Or should I rethink that measurement in femtometers or picometers? Now, the general rule of thumb is to go down. Go down to the smaller measurement and make it bigger rather than the other way around. Because the choice here, if I go on the nano scale, it would be 0.12 nanometers. And that's not bad. That's not a bad unit to go with. On the pico scale, however, 120 picometers. It's a preferential thing, but chances are pretty good that I can rationalize what 120 looks like a little bit better than what I can kind of picture 0.12 looks like. Are you technically wrong in either direction? No. You're not technically wrong keeping it in meters either. But if you're trying to kind of give yourself a context of what that looks like and how to compare that, having a little bit more tangible of a number to go to can help. And so, like I said, the kind of the key aspect there is to go down. Go down to the smaller level if I'm between two, and use that to convert it to a higher number rather than a smaller number. But like I said, you really can't go wrong in either direction. We're going to move into our first kinds of calculations. We're going to talk about some relatively simple calculations today. Calculations that, you know, if you use a calculator to do, it's certainly fine, but you could probably figure out a way to do them without a calculator as well. Because we're really just talking about sliding a decimal left and right in these conversions. There are two types of calculations that come about in chemistry. Two big idea kinds of calculations, at least. The first is the unit conversion. We're going to talk about unit conversions today. We're going to talk about unit conversions on Friday. We're going to talk about unit conversions next Wednesday as well. In unit conversion problems, we're basically just taking one set of units and turning them into a different set of units. Sometimes for cosmetic reasons, sometimes because we need to convert between metric and English, sometimes we just need to know more about things in terms of what we have available to us. But that's the unit conversion problem. The other type of calculation in chemistry is the equation problem. In the equation problem, you have to use some kind of specific equation to figure out what you're trying to know. So if I want to know how much energy is being generated by this chemical reaction, I'm not going to be able to do so using a unit conversion. I'm going to have to use an equation and integrate my experimental data into that equation, into that conversion. When it comes to unit conversion, we're going to use a technique known as dimensional analysis. Now, dimensional analysis works off of a very simple idea. In essence, to convert from one unit to another, we're going to use an equivalent comparison of the two units. And we're going to do so using multiplication and division. And it'll always be multiplication and division, never addition and subtraction. You can't add and subtract units from each other that aren't the same. So if I'm trying to figure out the mass of something, yes, I can take the mass of this object and subtract the mass of this object to figure out the mass of whatever's left over. That's perfectly fine. All the units there are the same, grams, grams, grams. But I can't take grams and subtract milliliters from it to get something else. It doesn't work. Nor can I add them together. The only way I can change from one unit to another is through multiplication and division. And so when we're doing dimensional analysis, it's really important that we do this technique and that we make sure that we keep track of our units as we go through the conversion process. Because we have to make sure that along the way, everything that's supposed to cancels out, and that we're left with what we're supposed to have at the end. And so at the kind of start of the process, this can be really difficult to kind of make sure that we're doing properly. That's why we do lots of practice. In our scheme, we're going to use what are called conversion factors. Conversion factors are ways of equating the unit that we have with the unit that we want. And what we do is we take those quantities of what we have and what we want, and we turn them into a fraction. And because the top of the fraction is equal to the bottom of the fraction, even though the numbers aren't the same, it's like we're multiplying by an equivalent amount. What happens when you multiply a number by 1? You get the same number. What happens when you divide a number by 1? You get the same number. That's the principle that dimensional analysis is built on. Because the numerator and the denominator are equivalent to each other, it's like we're multiplying by 1. Even though we're not multiplying by 1, it's like we're multiplying by 1 because the two values are the same. And if I divide, it's like we're dividing by 1. The two values are the same. The main idea, the main thing that we have to do is that whatever units we have to cancel out by the end of the process. So I need to make sure that all the units that I start with end up getting canceled out, and the unit that I'm interested in is the one that's left behind at the end. And so this is what I'm talking about with that idea of conversion. The conversion rate between centimeters and inches is that there are 2.54 centimeters in every inch. 2.54 centimeters in every inch. Those two values are equivalent to each other. Doesn't matter where I'm measuring, that value is consistent. But what that means is that my equation, my conversion factor, I can write like this: 2.54 centimeters divided by 1 inch. Since 2.54 centimeters and 1 inch are the same thing, it's like I've got a quantity that is equal to 1. So it doesn't matter if I multiply the 2.54 centimeters or divide by the 2.54 centimeters. The result will be exactly the same. I will be correctly converting so long as my unit cancels in the end. So here's an example. I have 44.7 centimeters. I'm turning it into inches. Since I have centimeters in the numerator here, centimeters have to be the denominator in my conversion factor, so that is flat. The calculation, 44.7 times the 1 divided by the 2.54 give me 17.6 inches. And so what I have done is I have converted 44.7 centimeters into 17.6. So what order we put these in ultimately does not matter so long as it serves the ultimate goal. And the ultimate goal is to cancel out the units that I don't like and leave behind the units that I do. Let's take a look at some examples here. First example, convert 3.55 kilograms into grams. Now, with any process like this, the first thing I want to do is I want to start with the information that I'm given. The information I was given here was 3.55 kilograms. Now, I want to turn this into grams, so I need a conversion factor. The conversion factor that I need is going to cancel out kilograms. So kilograms are going to go in the denominator of my conversion factor so that they cancel out. And grams is going to be in the numerator of my conversion factor so that it's left over. All I need now are the numbers that go into that. Now, if you don't know that off of the top of your head, you can go back to our prefixes here, and you can see that kilo means 1,000. So there are 1,000 grams in a kilogram. So I'm going to put that in here, 1,000 grams in 1 kilogram. Now, here's the part where if you're not so good at doing math in your head, go ahead and pull out your calculator. 3.55 times 1,000, you get 3,550. But if you recognize that we're talking just merely about factors of 10 here, again, going back to the chart here, 10 to the third. 10 to the third means that I can slide that decimal 3 spots over to the right. So I could have got the same answer, using mental math. 1, 2, 3 over, I would need to add a 0 to get 3550. Personally, doesn't bother me either way, whichever way you want to do it. If you do it in your head, though, make sure that you're right, because obviously it's a little bit embarrassing if you have to go, I didn't get this right. Well, why? I slid the decimal too many spots. That's a preventable mistake. All right. Convert 8,944 millimeters into meters. So again, start with what we have. And I want to convert millimeters into meters. So millimeters needs to go in the denominator. Meters needs to go in the numerator so that the millimeters cancel and I'm left with that meters. What's my conversion? So I go back to my metric chart. Milli is 1/1000. So a couple of ways that I can do this. I can do it like this, 10 to the negative third to 1, or the chart had it as 0.001. If you're using the chart, just make sure that you know that that value, whether it's in scientific notation or decimal notation, always goes on the base unit, not on the other unit in the metric system. Because those prefixes are all relative to the base. So if I do that, move the decimal 3 places to the left because this is a -3, I get 8.944 meters. Now, the other approach to this, if you don't like dealing with the decimals and the scientific notation, the other way that you could have done this was If you like working in hard numbers as opposed to decimals or scientific notation, you could easily convert that into numbers that are a little bit easier to put into your calculator. Just make sure that you multiply the numerator and the denominator by the same number when you do so. Or just realize that when it says 1/1000th, you can flip it around. So 1/1000th of a meter would mean that there are 1,000 millimeters in that meter. 1/100th of a meter would mean that there are 100 centimeters in that meter. You can kind of take it either direction. All right, let's do some more. In these ones, we are going to look at multi-step conversions. Now, in this one, we're asked to go between milligrams and kilograms. Now, my metric chart doesn't have a direct relationship between milligrams and grams, or excuse me, milligrams and kilograms. What do I do in that situation? Well, I have to do two conversions. The first conversion is between where I'm starting and the base. The second conversion is between the base and what I'm trying to ultimately find. So if I have 4,598 milligrams, my first conversion is to the base. So I want to turn the milligrams into grams. That'll cancel out the milligrams. The second conversion would be from grams to kilograms. So I want to take these grams in the numerator and cancel them out by putting grams in the denominator here. Now I just need numbers to go with it. So for the milligrams, it's the same thing. 1 gram is 1,000 milligrams. And then for the kilogram conversion, 1 kilogram is 1,000 grams. So in this particular conversion, I'm going to have to divide by 1,000 twice over. And so if you're sliding the decimal, you would slide it a total of 6 times to the left, 3 for the first, 3 for the second. If you're using your calculator, you just hit divide by 1,000 and you do it twice. 4598, divide by 1,000, divide by 1,000 again. And you get 4.598 times 10 to the negative third kilograms, or if you keep it in decimal format, 0.004598 kilograms. At this point, no. We are going to learn scientific notation on Friday, though. And so once we do that, there will be times where scientific notation is going to make more sense. The reason I put that one up first, my calculator turned it into scientific notation first. But depending upon your model of calculator, it might come out in decimal just as easily. For a number like this, it doesn't matter as much. When we get to the smaller scale and to the bigger scale of things, scientific notation is going to make more sense. But at this point, it's more about the process than the product. Are you calculating things correctly? Are you converting things correctly? All right, let's look at one last one here. 0.187 deciliters into milliliters. Now again, if I go to my metric chart here, I don't have a direct relationship with in milli. Now I can figure out what it is if I want to, but it might be just as easy to just do the conversion to liters and then take it from liters to milliliters instead. And so that's what I'm ultimately going to do. So first I need to turn the deciliters into liters. There are 0.1 liters in every deciliter. You can also flip that around. One liter has 10 deciliters in it. And then on the flip side here, I want to turn liters into milliliters. There are 1,000 milliliters in a liter, so the liters cancel out. And so to solve this, remember, if you multiply by all the by all denominator, so 0.187 multiplied by 0.1 multiplied by 1,000 would give me 18.7 milliliters. So that's as far as we're going to get for today. I had written into the original plan to do some extra practice problems, but I'll leave that for your I'll leave that for your homework assignment to see how you did with that. Before you go, I did send you one pair deck checkpoint, and that's just how did this go for you? How well do you think that you understand the metric system and metric conversions? Remember, I'm asking you the same question at the end of this assignment here in Master. So answer as truthfully as you can.